Hey, welcome back. We're working in 7.3 now, and more translations or Laplace transforms basically. Again, with the first translation theorem, so s-axis translation. And here we go. So, first translation theorem. It's pretty simple. It's kind of hard to remember all the time when you have like 20 balls in the air and you're juggling them all. But basically, you have the Laplace of some exponential function times whatever function, some f of t function. And to evaluate that, it'll come down to a substitution. So you'll rewrite this as Laplace of f of t, where at the end, after you do the Laplace transform, you're going to replace the s part with a shifted s. Okay, so you'll draw this bar, write s, arrow, s minus a. Okay, so at the end, you'll have f of s evaluated by replacing s with s minus a, and so you'll end up with f of s minus a. Okay. All right, so it's pretty simple. The proof is pretty simple. You're just doing a substitution, basically. Visually, you could see it as a shift of the original transform on the s-axis over by a. Let's look at example 1. So first I have Laplace of e to the 5t times t cubed. So what you kind of do is just kick out the 5 to the t part, e to the 5t part, and you just kind of consider Laplace of t cubed. So you got to remind yourself at the end, replace s with s minus 5. Okay. So Laplace of t cubed is going to be in the denominator s to the 4th, and then 3 factorial in the numerator. And then you just place s with s minus 5. And you get 3 factorial all over s minus 5 to the 4th. Okay. And that's what you would think of if you're thinking in terms of annihilators. So what would annihilate this? It would have to be like d minus 5 to the 4th. Okay, so in the denominator, you'll see the annihilator. In the numerator, you're kind of on your own. You kind of have to still, but at least, knowing the stuff we know about annihilators and how they're related to the transforms, you can check. You can check part of it. Okay, let's look at the other one, part B. So the Laplace of e to the negative 2t cosine 4t. With regards to the annihilator, the roots would have been negative 2 plus or minus 4i. I know usually I say d minus negative 2 plus 4i times d minus negative 2 minus 4i, but another way of getting the annihilator is just move the 2 over. So you get m plus 2 is plus or minus 4i. Square both sides, you get m plus 2 squared equals 16. And so you'd end up with m plus 2 squared, which would be minus 16, right? And then plus 16 equals 0. So the annihilator there is the d plus 2 squared plus 16. And that's what you should see in your denominator. Okay. So you can kind of check again. But anyways, using the translation theorem, just kind of kick out the e to the negative 2t. You have cosine of 4t, but you got to remind yourself to translate at the end over s minus negative 2, so s plus 2. Okay. So Laplace of cosine, of course, is s all over s squared plus k squared. And then you need to translate. So you'd end up with s plus 2 all over s plus 2 squared plus 16. Okay. Going in the reverse direction, you kind of have to work inside out. Like here, we worked. We kicked out the e to the t into the Laplace, and then at the end, you do your once you're done, you do the transform. It's the opposite when you do the inverse. So part 2, the inverse of the translation, first translation. It may be easier just to show you an example, but the examples are kind of nasty. So I'll just give you the theorem. So you have Laplace inverse of some expression that you could tell has been translated So what you'll do is kind of kick out an e to the at, and then consider the Laplace transform of that thing shifted over. Okay, so just f of s would have been replaced by s minus a here. Okay, and then figure out the Laplace inverse of f of s, which should be a to the t, or f of t. Okay, so let's look at the maybe some problems like in the book and sorts. We'll start back at in the beginning, and then we'll kind of work our way up there. So the first one, we'll look at number 3. I have Laplace, so not Laplace inverse, but just Laplace first. E to the t plus e to the 5t squared. So this will be the Laplace. Go ahead and FOIL that junk out. So you get e to the t times e to the t is e to the 2t. Add the exponents. Plus 2e to the 6t, and then plus e to the 10t. You can then distribute, so you get t e to the 2t plus 2t e to the 6t plus t e to the 10t, and then do your sort of shifting here. So this will be Laplace of t, but you have to remind yourself shift s over to s minus 2 plus 2 Laplace of t, where we're shifting s over to s minus 6. So that minus 6, that's based off the exponent. Okay, so if you see an e to the 6t, the shift is going to be s minus 6, and then plus Laplace again of t, and the shift here is s over to s minus 10. All right, so what is the Laplace of t? That's just 1 over s. Whoops. And this third guy is 1 over s as well. But we have to do all of our substitutions now. So basically the shift on the s-axis. So get 1 all over s minus 2 plus 2 all over s minus 6 plus 1 all over s minus 10. Oops, these should all be squared, shouldn't they? It's Laplace of t, not the Laplace of 1. Okay, so this will be squared. Sorry about that. All right. Let's look at another guy. This is maybe number 5. Looks annoying. So I have Laplace of, let's go ahead and distribute the cosine, right? So I have cosine 4t minus e to the t, cosine 4t plus 5e to the negative 2t, cosine of 4t. And what do we get? So I have Laplace of cosine of 4t, that's s all over s squared plus 16 minus. So this part is going to give you a shift of s minus 1. So let's get the Laplace of this portion. So it'll be s all over s squared plus 16. Then I have to do the shift. And then plus 5 times the s all over the s squared plus 16 with a shift of s to s minus negative 2, so s plus 2. Then you just do your substitutions. I apologize, I did skip kind of one intermediate step where I'm rewriting everything by kicking out the, the second term minus Laplace of just cosine of 4t, but then I have to shift the s over to s minus 1. So I'm skipping that little part, hope you don't mind. Minus s minus 1 all over s minus 1 squared plus 16 plus 5 times s plus 2 all over s plus 2 squared plus 16. Okay, not a big deal. It's just mostly just memorizing and stuff like that. Okay, let's look at Laplace inverses then. So like number 6, Laplace inverse of 1 all over s plus 5 cubed. So it looks like it's been shifted over, right, by that that plus 5 is the shift. So it's like s minus negative 5 in reality. And so we're going to undo that shift. So I have 1 over s cubed, where we think the shift was s to s minus negative 5, so s plus 5. Okay. And then I can't technically do the Laplace inverse yet. I need to multiply top and bottom by 2 factorial, right? And then I'll factor out the 2 factorial. So 1 over 2 factorial, and then we have a 2 factorial in here, all over s cubed. You can pull the s to s plus 5 out by just kind of remembering I have to do a shift, but the Laplace transform of 2 factorial over s cubed is going to be t squared, but then I have to shift the thing, right? So what the heck did I do? The shift part is the e to the, sorry, e to the 5 negative 5t, or just e to the 5t, sorry. No, e to the negative 5t, that's right. Okay. And yeah, okay. Let's do another one. Those are hard. 7, or maybe even try number 8. Let's get the Laplace inverse of s all over s squared plus 6s plus 10. I mean, they're hard on your brain, you know. It's like, oh, I got to do this and this. I think if we kind of do some tricky work to the denominator, we'll see it's probably some sort of shifted. So completing the square is always beneficial. S squared plus 6s plus 6 over 2 is 3. 3 squared is 9. Immediately subtract the 9 plus 10. This will be a Laplace inverse of s all over s plus 3 squared plus 1. So it looks like it's been shifted over by 3. In order to make that a reality, though, I need to add a 3 into the numerator. So it would be s plus 3 and then minus a 3 all over the s plus 3 squared plus 1. And then I'm going to have to split that into 2 fractions, right? So Laplace inverse of s plus 3 all over s plus 3 squared plus 1 minus 3 all over s plus 3 squared plus 1. So that first guy's a cosine. The second guy's going to be a sine, right? So anyways, let's take a look. Laplace inverse of s all over s squared plus 1, where we're doing the shift to s over to s plus 3, minus, we could kind of factor the 3 out of the inverse Laplace there in a sec, but anyways, it'll be 3 times 1 all over s squared plus 1 with this translation s over to s plus 3. Okay, and parentheses out here. Then we could start chipping away. So that first guy, there's from the shift, this part, there'll be an e to the negative 3t. And then this part is the cosine of t. And then minus 3. And again, you can kind of pop out this shifter part, which is the e to the negative 3t. And then the rest of it is just a sine, right? Sine of t. Oops, get back to black here. Sine of t. Okay. Great, good stuff. They get more and more complicated, especially if you got to start doing by parts. So like number 10. The Laplace inverse of 5s minus 1 all over s squared times s plus 1 cubed. Org. Sometimes you could do some tricky kind of stuff to simplify the partial fractions, but sometimes you just have to grin and bear it. And I think I'm just going to have to grin and bear this one. Okay, so I have s squared, that's s plus 1 cubed. Okay, so hopefully I'll get it right. I do kind of have like ways of checking my work, so I hope you do too. I mean, you got to do them by hand, but you know, honestly, you're going to make mistakes, and if you don't have any friends to check your work, you should probably have a computer to check your work, right? So if you just type in partial fractions and then type in the fraction and hit enter, Wolfram will do your partial fraction for you. So you can see it right there. But I'm going to show you, I'm going to do it by hand. So anyways, I have a over s plus b all over s squared plus c all over s plus 1 plus d all over s plus 1 squared plus e all over s plus 1 cubed. Multiplying through, I'll have a times s plus 1 cubed is s cubed plus 3s plus 3s squared plus 3s plus 1 plus b times s plus 1 cubed is s cubed plus 3s squared plus 3s plus 1. I mean, you literally have to FOIL it out. I just know it from Pascal's triangle, right? 1, 3, 3, 1 are the coefficients on that. Anyways, moving on to c, so plus c, we'll need an s squared, and then s plus 1 squared is s squared plus 2s plus 1 plus d s squared times s plus 1 plus e s squared. Okay, so I have 5s minus 1 equals as to the fourth plus 3as cubed plus 3as squared plus as plus bs cubed plus 3b squared plus 3bs plus b plus cs to the fourth plus 2cs, butchered that one, 2cs cubed plus cs squared plus ds cubed plus ds squared plus es squared. And then you start equating coefficients. So the fourth powers, I have an a, a c, and that's it. That must equal 0. Then the powers of 3, so I have 3a plus b plus 2c plus d equals 0. Then the powers of 2, 3a plus 3b plus 2, whoops, I almost screwed that up, plus 1c plus a d equals, oh, and plus an e. Oh, we're all getting in on the action, huh? Equals 0. And then that was the s squared. So for the s's, I have 5 equals a plus 3b. And there's no more s's after that. Seems like there should be. Okay, well, anyways. And then for the constant term, -1 equals b. So you get 1 for free. B is -1. Then you can start back subbing. So 5 equals a minus 3. So a equals 8. Okay, and you can kind of check as you go along, like I have my Wolfram Alpha. So the a, I'm saying is 8. So you should see an 8 over x. Yes, I do. The b is -1, so -1 over x squared. I see that. Good. So I must be on target. I can get c. 8 plus c equals 0. So c is -8. Let's make sure that's right. -8 over x plus 1. Yep. And then looks like I have 24 minus 1 minus 16 plus d equals 0. So we have 8 minus 1 is 7, so d is -7. So it should be -7 over x squared plus 1, yep. And then finally 24 minus 3 minus 8 minus 7 plus e equals 0. So it's 10 minus 18. So 6 plus e equals 0. So e equals negative 6. So we should have negative 6 over x plus 1 cubed. And I think I got them all. Okay, so let me rewrite this monster. So I have where I need the Laplace, was it an inverse Laplace? Of course, because we're in terms of s. So inverse Laplace of 8 over s minus 1 over s squared minus 8 all over s plus 1 minus 7 over s plus 1 squared minus 6 all over s plus 1 cubed. Okay, and then we could start doing some shifting and all that good stuff. So this guy and this guy we can do. The first one is just 8 and then minus t. This one you could just think of annihilators. This is going to be negative 8 e to the negative t, right? You could do a shifting, but it's not necessary. And then minus 7 times Laplace inverse of 7, whoops, I already factored out the 7, sorry, of 1 all over s squared, and of course we're doing the shift s to s plus 1, so I'll have to pop out an e to the negative t, and then minus 6 times Laplace inverse of 1 all over s cubed, where the shift again is s to s plus 1. And then we'll have 8 minus t minus 8e to the negative t minus 7e to the negative t. Okay, so again, you're always popping this part out as an exponential. And then Laplace inverse of 1 over 7 squared is just t. And then minus, well, we need to kind of normalize this one. In the numerator, I need a 2 factorial. So you're going to have to divide the outside part by 2 factorial, which is just 2. So that would be minus 3. And then you need an e to the negative t. And of course, t squared is inverse Laplace transform of 2 factorial all over s cubed. So let's make sure we got the correct answer. Minus t minus 8e to the negative t minus 7e to the negative t minus 3e to the negative t squared. Okay, great. Now we're going to start solving differential equations with the Laplace transform. Let's try, number 13 looks quite annoying. It's a reason at this point in life not to do it, right? Let's try number 14. Okay. See how that goes. So y double prime minus 6y prime plus 13y equals 0. Y of 0 is 0. Y prime of 0 is negative 9. Okay, so you do the Laplace transform of everything. I'm going to get s squared, Laplace transform of y, minus s times y of 0, which is 0, minus y prime of 0, which is negative 9, minus 6 times s times the Laplace transform of y minus y of 0, which is 0, and then plus 13 Laplace transform of y. The Laplace transform of 0, if you think about it, if you go back to the definition, right, it's just 0 to infinity of 0 times e to negative st dt, right? But that's just going to be the integral of 0, and that's going to end up being a big 0. Okay, the area underneath the graph of y equals 0 is 0. So it'll equal Laplace of 0, but that's just equals 0. Okay, start collecting all your Laplace stuff together. So you end up with an s squared from this guy, a negative 6s from that guy, and then a 13 from that guy, times the Laplace of y. And this will be 0, so you have plus 9 to move to the other side. And then this, you got a 0 there, so nothing there. And then Laplace of y equals 9 all over this junk, which I think we're going to have to probably complete the square, right? So s squared minus 6s. Negative 6 over 2 is negative 3, and then squared is plus 9, minus 9 plus 13. Okay, so Laplace of y is going to equal 9 all over s plus, or rather s minus 3. S minus 3 squared. And then negative 9 plus 13 is plus 4. So Laplace inverse on both sides, then y will equal Laplace inverse of this thing. I need a k value up top. It's also going to need to be shifted. So anyways, I can factor out the 9. I'll have 1 all over s squared plus 4. If you consider the shift, s goes to s minus 3. Okay. I'm going to plop out the e to the 3t. And what else? Then the Laplace of 1 over s squared plus 4, the Laplace inverse of that, you need to kind of get that k value up top, so you need a 1/2 out as well. So you could write times 1/2 times, what is that, a sine then, a sine of 2t. Okay, so y equals 9/2 e to the 3t sine of 2t. Okay. I lost a negative somewhere. Where did I lose it? Oh, right here. Should be negative. Sorry. Negative. All right. You see down here, we're going to get into something new. So the next section are what they call shifts on the, I guess on the t axis then, and it'll come down to this new piecewise object that we're going to need if you want to work with kind of electronics. So this is now translations on the t-axis. Okay. And basically it'll result in an exponential when you are doing, let me see if I can find kind of the formula here. Yeah, so when you're doing Laplace transform, an exponential will pop out. As you know, here when you're doing Laplace inverse, an exponential will pop out. But this will kind of be like the reverse. So it's a bit difficult in that way, just reminding yourself which way does it go. That's a bit annoying. But it's really cool stuff. This unit step function is kind of what we need first. And it'll allow us to kind of produce graphs where the thing is turned off and then the thing is turned on. So firstly, the unit step function is defined as u of t minus a equals 0 when t is less than a and greater than 0. So we'll only assume t is going from 0 to infinity. We only care about positive time units. And then it's on when t is greater than or equal to a. Okay, so to graph this thing, I'll put it in red. So it's 0 from 0 to a. So maybe this is some point a here. And then it kind of gets turned on, right? So it jumps up to 1 at a. And then it'll just keep on going on from there. You could use this thing to graph other kind of cool functions. So for example, this guy right here, the piecewise function that they want, did they even give it to you? 7.3.3, where the heck is it? I don't want to look at it. 7.3. Okay, so they want in this I don't really think they give it an example number, but in this figure 7.3.2, what they're doing is they want to graph, 7.3.3, not 3.2, sorry. They want to graph something that is kind of, they want it to be off at first, And then when it turns on, they want it to be a linear function with slope. Okay, so in particular, they want when it turns on to be f of t equaling 2t minus 3. Okay, so how do I pull that off is kind of the question. And so once you get to 1, so let's say this is 1, they want this function to be turned on. So f of 1 would be, 2 minus 3, which is negative 1. So it'd be right here. And then it has slope go up to 1, 2 over 1. So you just use the slope to get to the next point, and it would go in like that, okay, from that point on. So I want a formula for that picture. Okay, so it's 0 first, and then it gets turned on, and it's this linear function. How do I pull that off? Okay, so u of a, in this case, we want it to turn on at 1. So I'm going to put u of, not a, but t minus a. Our a value is 1, right? So it's going to be, this thing will be off at values less than 1. And then we hope to turn it on to something when it gets to 1. Right, so t greater than or equal to 1, we want it turned on. So the function that does that is just u of t minus 1 times f of t. So you'd have 2t minus 3 times u of t minus 1. And if you think about it as just multiplying the pieces, if you multiply 0 times 2t minus 3, you get 0. And then if you multiply 1 times 2t minus 3, you get 2t minus 3. And this is exactly what we want, right? This is for t greater than or equal to 1. Okay. As far as I can tell, there's no kind of like standard way for building these functions. It's just kind of being clever enough to get it to work. So for example, this one right here, this 7.3.4 we want to build. So figure 7.3.4 has 2 parts to it. So first it's at, so let me put some tick marks on here before I screw around like I did last time. Okay, so first I want it to be up at 2, from 1 to 2, right? And then I want it to drop down to negative 1, from 2 to 3, and then I want to go to 0 from 3 on. So how do I accomplish that? Well, you could start by just having 3, the function 3, okay, with no cause for anything weird. So f of t would be 3, and what you would get basically is just a horizontal line at 3. 1, 2, 3, it's this. Okay, but then once you get to 2, you want it to jump to negative 1, right? So what you do is kind of turn on another piece of the function. You're going to turn on this other piece, which will be a minus 4 at 2. So you go t minus 2, and this part will then turn on. So as it sits right now, it'll be 3 at first. So f of t will kind of be in piecewise form. It's 3 from t greater than 0 but less, greater than or equal to 0 but less than 2, and then you're turning it on. So let me maybe erase f of t. It'll be yes, yeah, it is. So it is f of t, and then at some point it gets 3 minus the 4 part here. It's not a very good job of describing it. So at t equals 1, 2, this part gets turned on. So in this region, it's just f of t equals 3. And then once you get to 2, this thing gets turned on, so it becomes a 1. So at first it was f of t equals 3 minus a big 0 because it's not on yet. And then once t gets to 2, it gets turned on, so it'd be 3 minus 4, which is negative 1. Okay, so it will jump down to here and keep going. Then we want it to go to 0 at 3. All right. So how do I get that to happen? So you have to kind of imagine there's another function, right, that's not on. So plus some other thingamajig, which gets turned on at 3. So you go u of t minus 3. And what do I need? I need it to go back to 0, so just one of those, right? So at 2, it's not on yet, so it would be a 0, so it would be -1. But then once you get out to 3, it'll get turned on, so you have 3 minus 4 plus 1, which will be just 0 at that point. Look, okay, so it's not the most intuitive thing, but once you get the hang of it, it's like riding a bike. It's super easy. Let's look at example 5. Okay. So here I have f of t equals, I want 20t at first, from 0 to 5. And then I want 0 from t beyond that, right? So basically you're starting with just 20t. And then there's this part which you kind of assume is not on. It's a 0 part, right? But when it gets turned on at 5, you want it so it gets rid of the 20t. So when it gets turned on at 5, you need it to get rid of 20t. So why not just make it minus 20t? And then as soon as it gets turned on, it'll be 20t minus 20t, because that u of t minus 5 will be 1, and that'll just equal 0. Okay, so, and that will turn out to work. Okay, anyways, we want to consider the Laplace transforms of these things. And the second translation theorem here, the kind of first look at doing these transforms. So did I have a section? This, I think it's section 2. So theorem 7.3.2, which is a second translation theorem. Basically just says that if your function is shifted over nicely in the same way as this step function, you can figure out the transform by just, you can get rid of the u of t minus a part by kind of replacing it on the outside with an e to the negative as. Okay, and then you're just thinking of f of s. Okay, the trouble with this formula is that oftentimes this f of t minus a will not be in that form. Okay, it's rarely going to be in that form. So what you'll see in the book is this kind of second version, and I prefer just to give that to you now rather than waiting. Okay, so you generally see it like this. You're trying to do Laplace transform some function times the step function, and to pull that off, it'll be e to the negative as times the Laplace of f of t plus a. All right, and that turns out to be more useful than I think this original one. And they wait to give you that version in the book until later on after they give you the inverse. Where the heck is it? So yeah, here's the alternate form. It's right here. Okay. Okay. The proof of why it works is basically all you're doing is kind of shifting over the definition. So the proof, which may or may not be helpful, you have 0 to infinity of e to the negative st times f of t minus a times u of t minus a dt. This object right here at first is off, right? So from 0 to a, it'll just be equal to 0, so that integral will be 0. But then it turns on once t is greater than or equal to a. So this integral becomes the integral from a to infinity of e to the negative st times f of t minus a dt. And then you could do a u sub on the thing and let u equal t minus a. In other words, t will equal u plus a, and of course a what the heck will a be? A will be t minus u or actually, let's think about it a little bit better. All right, so this integral right now is going from t equals a to t equals infinity. Right, so if you plug in t and you want your new integral in terms of u, going from u equals something to u equals something, u of a, so plugging in a for t, will be a minus a, which will be 0. So what you're going to end up with is kind of like basically a transform, the definition of the transform of e to the negative, instead of st, we'll have negative s times u minus s times a times f of t minus, instead of t minus a again, you just have f of u, and then du, right, because du is just going to be dt. And then you could rewrite that by factoring out this part, right? So just using your rules of exponents, that will be e to the negative sa times the integral from 0 to infinity. And let's change u back into t, and you'll see we'll have basically a Laplace transform of f of t, right? So e to the negative st f of t dt, okay, which is of course then equal to e to the negative sa times the Laplace transform of f of t, and that's kind of what we were saying above. Okay, right. So it's, where is it? Right here. Okay, so it's basically just, if you see, if you have to do a transform of one of these stepwise functions, you just kind of pluck out a e to the negative sa and then do the transform of f of, well, you're usually going to have to do t plus a, as in this form right here. Okay. Anyways, the inverse of the second translation theorem, then we're going to need that for pulling this off. So where the heck is the inverse form? Let's see what section I'm on in my notes. 2, so 3. The inverse of this guy, this time e to the negative as, and then you have some function of s. That'll equal, you kind of just, I would just pull out the stepwise function first and write that. So u of t minus a, and then you're doing a Laplace inverse of this f of s thing, and when you get it, you're going to shift it. Okay, so instead of writing, like if you had, for example, Laplace inverse of, and I'm going to show you some examples, but I don't know, e to the negative 3s times 1 all over s. This would be u of t minus 3 times, the Laplace inverse of 1 over s would normally just be, well, let's make it a little harder, right? 1 over s squared would just be t, but because we have to translate it, it's going to be t minus 3. Okay, so it's a bit weird, and it'll take a bit getting used to, but there's the formulas. Let's dive into the homework and fiddle around with that, shall we? Okay, so number 16, doing a Laplace transform of t minus 1 times u of t minus 1. Okay, so this one is kind of set up for you. Like I said, usually you'd have to do a bit of work, but this will be e to the negative s times the Laplace transform of t. Okay, and then that will be e to the negative s times 1 over s squared. Okay, so it's basically whatever this thing is, you end up having to add in 1. So to rewrite it, it would be t minus 1 plus 1. Is kind of how I would approach that. So for number 17 then, we have Laplace transform of t times u of t minus 5. So immediately kind of pop out the e to the negative 5s, and then you have a Laplace transform of not t, but you have to shift it, right? And you have to make it t plus 5. Okay. Or at least that's what you're going to be thinking once you get done with it. You have to, yeah, t plus 5. Okay. Okay, so you get e to the negative 5s, and then Laplace of t is 1 over s squared, and Laplace of 5 is 5 over s. Okay. Let's do another one. Here we have 18. Laplace, and you may want to like pause the video and see if you can get it and then unpause it, but this one. Okay, so immediately I'm going to pull out the e to the negative s and then do the Laplace on this thing, and I'm going to replace the t with t plus 1. So if this thing is t minus a, you replace the t and the f of t with t plus a. Okay, so you have 6 times t plus 1 plus 1. That'll be e to the negative s times 6 all over s squared. So I'm kind of doing some in my head. 6t plus 6 plus 1 is 6t plus 7. And then plus 7 over s. Okay. So some of these are pretty weird, especially when they want you to put, so now getting into the Laplace inverses, they want you to put something in that first box, and I don't know what the heck they want you to put in there. Maybe somebody teaches it differently, but I always just end up putting 0 in that first box. So anyways, let's try number 21. Maybe next year I'll figure out what the heck that box is for, but assuming I'm still teaching this next year. But what do we have? E to the negative pi s over s squared plus 1. Okay. I need to do Laplace inverse of this, so that numerator automatically you can kind of pull that out and get your u of whatever. So this would be u of t minus pi, and then for the rest of it, it's kind of business as usual, but you have to do a substitution of t minus pi into whatever the heck the function is, right? So this looks like it's going to be a sine function, sine of t, but you can't write sine of t. You have to write sine of t minus pi. Okay. Then you can simplify that, and you can see to the right there, I didn't write sine of t minus pi. I wrote sine, negative sine t. How do I get that? It's from the sine formulas, and I call it the couscous formula. So the sine formula, I call these the same sine formulas. So it'd be sine A cosine B plus, because it has the same sign, plus sine B cosine A. And then sine of A minus B, same thing but with the same sign. Okay, so sine A cosine B minus sine B cosine A. Then the couscous formula, I call it couscous because it always has cosine first. So cosine A cosine B, and it's not the same sign, it's opposite sign. So plus, whoops, that's not the opposite, is it? So it'd be minus sine A sine B, and then cosine of A minus B. It's the same thing but with a plus. Okay, so sine of t minus pi is going to give you same sine formula, sine of t cosine of negative pi, and then whatever, because that whatever stuff's just going to be the sine of negative pi, which will be 0. So I know that rest of it's going to be 0. Cosine of negative pi is -1, so this will be negative sine t. So you could simplify it. On a test, I don't expect you to have all those memorized. I just have them memorized because I teach the class. So it's negative sine t times u of t minus pi. The software may allow you to just write sine of t minus pi in there, but as you see, I have negative sine t. It's of course 0 plus negative sine t u of t minus pi. Okay. Let's try another one. It's 23. So Laplace inverse of e to the negative s all over s times s plus 1. And right, so it seems like probably here you're going to have to do some partial fractions. So 1 over s times s plus 1 is equal to a over s plus b all over s plus 1. And then you can multiply through by everything. 1 equals a times s plus 1 plus bs. Let s equal -1, so you get 1 equals negative b, so b is -1. Let s equal 0, you get 1 equals a. So this will become the Laplace inverse of e to the negative s times 1 all over s minus 1 over s plus 1. Okay, and then the heavy side part, or sorry, not heavy side, the step function part is u of t minus 1, and then for these other parts you have to translate them by t minus 1, right? So the first one is just 1. 1 translated by t minus 1 is still 1, right? So if your function f of t is equal to 1, f of t minus 1 is still equal to 1. It's like duh, right? It's too obvious. Anyways, the other guy looks like a shifted version on the s-axis. Of course, that's just e to the negative t, but then you have to shift the t, right? So it'd be e to the negative t minus 1, like that. It's kind of annoying. Okay. Anyways, they have some problems where they're trying to get you to build the functions based off the graphs. Here's another one. Write the function in terms of the unit step function. What is this? Number 26. I want f of t equals 3 and then -4, right? From 0 to t to 7, and then t greater than or equal to 7. So first I want it to just be 3 plus something that's turned off. So then at 7 I want that other part to turn on. So plus something turned on at 7. So to make everything -4, I'm going to have to go -7 right here. Okay. Then they want you to get the transform of that. So Laplace of this thing is the Laplace of this thing. And so that will equal, Laplace of 3 is just going to be 3 over s minus 7 times the Laplace of u of t minus 7. So that's going to be e to the -7s, and then a shifted version of 1, right, which will just be 1 over s. Okay, so you would get that for your translated version. Let's try number 28. So I have f of t equals t and 0, 0 less than or equal to t less than 7, and then for t greater than or equal to 7. So at first I want the t part turned on plus something that's not on yet. And then at 7 I want t plus, well, basically negative t, right? So I'll turn on the negative t at 7. Okay, then I need to do the Laplace of that. So the Laplace of t is no big deal. That's just 1 over s squared minus the Laplace of this rest of this stuff. So you'll have an e to the -7s, and then the Laplace of t, but you have to, what do we have to do? We have to, so you have to add 1 to it, right? So it's really the Laplace of, and I already factored out the -1, so it's going to be a t plus 1. Okay, so this will be 1 all over s squared minus e to the -7s times 1 all over s squared plus 1 all over s. And I lost a 7 in there somewhere. Where did I lose my 7? Oh, it's t plus 7, sorry. Yeah, right there. So if it used to be t minus 7, you had to put a t plus 7. Okay. Those. Okay. Finally, the punchline is you actually solving one of these, using Laplace transform to solve one of these things. Let's try, I guess, number 31 here. Let's kind of make this the last one in my lecture. Y prime plus 4y equals f of t. Y of 0 is 0, so f of t is turned on at t, and then they want the t turned off at 1. Okay, so Laplace transform of that thing, we have s Laplace of y minus s times 0 plus 4 Laplace of y equals Laplace of t is 1 over s squared minus, get the e to the negative s part out, and then you're doing Laplace of t. Instead of minus 1, it goes plus 1. So you have collecting the s stuff together and factoring out the Laplace of y of s plus 4 Laplace of y, this part is 0, equals 1 all over s squared minus e to the negative s times 1 all over s squared plus 1 all over s. Then divide everything by s plus 4. So I get the Laplace of y equals 1 all over s squared times s plus 4 minus e to the negative s all over s squared times s plus 4 minus e to the negative s all over s times s plus 4. Then you got to do some partial fractions on all three of those. So the first two are the same, s squared times s plus 4. That will be a all over s plus b all over s squared plus c all over s plus 4. So 1 will equal a s times s plus 4 plus b times s plus 4 plus c. Let s equal 0. You get 1 equals, whoops, this should be c times s squared, right? S is 0, so you get 1 equals b times 4, so b is 1/4. Let s equal negative 4, so you get 1 equals 16c, so c is 1 over 16. Let s equal, 1, you get 1 equals a times 5 plus 1/4 times 5 plus 1/16 times 1. So I'll have 1 equaling 5a plus 5/4 plus 1/16. Find a common denominator there. 1 equals 5a plus 21/16. So 16/16 minus 21/16 equals 5a, which totally seems wrong. It'll be negative 5/16 equals 5a, so a equals negative 1/16, I hope. The other one, 1 all over s times s plus 4 equals a all over s plus b all over s plus 4. So 1 equals a times s plus 4 plus b times s. So let s equal 0, you get a times 4 equals 1, so a equals 1/4. Let s equal negative 4, you get 1 equals negative 4b, so b equals negative 1/4. And then we want to rewrite everything. Okay, so it's going to be y equals Laplace inverse of a negative 1/16 all over s plus 1/4 all over s squared plus 1/16 all over s plus 4. Then there's going to be a bunch of step functions, e to the negative s times the same thing, basically. Negative 1/16 all over s plus 1/4 all over s squared plus 1/16 all over s plus 4. Then minus e to the negative s times 1/4 all over s minus 1/4 all over s plus 4. And then you got to do the inverse Laplace on all that jazz. So y will equal negative 1/16 plus 1 force t plus 1/16 e to the negative 4t minus, and there'll be this step function here, t minus 1. And then inside of all these guys, you got to shift them over, right? So negative 1/16 shifted over to t minus 1 is just the same thing because it's just a constant function, plus 1 force times, it would normally be t, but I have to shift it over to t minus 1. And then plus 1/16 e to the negative 4. Again, I have to shift t to t minus 1. And then minus u of t minus 1 again times 1/4, shifting just 1 over, it's just going to be 1/4, minus 1/4 e to the negative 4 times t minus 1 again. Can't believe those are both shifted the same. Then you can kind of combine some like terms in there. It's going to be y equals negative 1/16 plus 1/4 t plus 1/16 e to negative 4t. You know, there's a negative 1/16 here. There's a negative 1/4 from the distribution. This 1/4 will cancel with this 1/4, so those will be gone. So you have minus u of t minus 1. I'm sort of combining all the junk in both of those parentheses together. So I'd have negative 1/16, and then I could combine these two, I believe. This will be 16. Oh, but they're minuses, right? So it'd be minus 1/4. That'd be plus minus. Oh, crap. So it's, but there's a minus on these as well, so it'd be kind of the same sign. So it'd be, yeah, okay, we're cool. I could factor this thing out. Yeah, we're good. We're good. So then plus 1/4 t is sitting there, and then combine those exponential parts together. So originally it was 1/4, now it'll be 4/16, so minus 3/16 e to the negative 4 times t minus 1. Blah. It's like there's no way that's right. You know, you just get that way after a while. My answer is, I believe it's the same. It's just the, you know, 1/16 e to the 1/4 t, negative 1/16, and then I combine the negative 3/16. Whoops, is that right? Oh, I see what I did. I didn't distribute the negative 1/4, but if I did, it would be negative 3/16 plus negative 3/16 plus 1/4, which is 4/16, which is positive 1/16. Definitely positive, right? Which isn't what I want. I want negative 1/16. So it'd be, well, it's in there somewhere. I think I made a little mistake. Hopefully you can live with that. You know, hopefully you get the idea, if nothing else. So I must have made it. I don't know what the heck I did. I'm sure it was somewhere in there. Negative 1/4 and then plus the 1/4. Those would cancel. This is driving me nuts. Negative 1/16. Is that right? Oh, and then if I distribute the negative, yeah, so it would be plus, and then this would be plus, but then that would be, yeah, so that's negative. Okay, it's right. It's just they distributed the negative, whereas my negative is still sitting out here. Okay, so you would get positive 1/16. Okay, so that's it. The hard part is just remembering all the ways that you have to transform stuff. And what I said, you know, make those flashcards. I think that's the best way to go. Okay, well, anyways, thank you for watching, and I'll see you next time.